My name is Sam Christian. I'm a senior at the Liberal Arts and Science Academy in Austin, Texas. For my Regeneron STS project, I observed an alignment between wide binaries and the exoplanets that reside in them. In astronomy, binary star system is two stars that orbit around each other. When these stars are far apart, we call them wide binaries. Exoplanets, or planets outside our solar system, can reside in these wide binary systems. The exoplanets I used for my study are from the TESS satellite. The TESS satellite observes the light curves of stars, or light over time from these stars, and it observes a dip in brightness that corresponds to a planet kind of blocking some of the brightness from the star. So the geometry of these systems is such that most or all these systems will be kind of aligned with the plane of the sky. We call that having 90 degrees inclination. The planets in this sample will also, from the TESS satellite, will also have very short periods. So the period of our Earth is 365 days. These will have periods of around 10 to 30 days. The wide binaries in my study were from the Gaia spacecraft. The Gaia spacecraft observed the relative motion of stars over time, and from this relative motion, previous studies have inferred wide binaries. So I kind of found a sample of 80 wide binaries on the Gaia spacecraft with exoplanets from TESS, or exoplanet candidates, I should say. So the first thing I did was find the masses of these systems. I used something called the isochrone fitting technique, where I fit the observed spectroscopy and of these systems to synthetic spectra to find masses. I then compared my estimations against previous techniques, and I found a relative alignment which suggests that my technique was successful, and I also had lower error bars than the past techniques. The second thing I did was map the orbital parameters. So we already have the relative motion of these stars in the sky from Gaia, but to find more intrinsic parameters, such as inclination, some major axis, eccentricity, and period, I used kind of a Monte Carlo sampling technique called LOFTY to find probable orbits of these systems. So as you can see, I have a pretty good tight fit from these systems. The parameter I was particularly interested in was inclination. I mapped the inclination of these wide binaries compared to the inclination of the exoplanets to find the relative inclination, which tells us the alignment of these systems. I then observed that most of the systems tend to be aligned, which is a previously unobserved effect. And this alignment, I should mention, is compared to a control sample of wide binaries without exoplanets. So to explain this previously unobserved alignment, I came up with two theoretical effects. These theoretical effects have been theorized to exist in these exoplanet systems and wide binaries, but have never really been observed. There's not a lot of observational evidence for them. The first is the Light-Kozai effect, which is essentially an oscillation between the eccentricity, and which is kind of how squished the orbit is, and the inclination of the orbit over time. This oscillation can lead to a preferential alignment for what we'd expect to be an initially random distribution in the alignment between exoplanet and wide binary, technically the spin axis of the star in the wide binary. So this Light-Kozai effect we'd expect to only see at small timescales, or small times over the Light-Kozai effect acting, because the Light-Kozai effect can only exist when the disk, or the stellar disk where the planet forms of the star, when that exists on scales of around 1 million years. The disk timescale, which is a precession of the disk of the star over time, that can also lead to preferential alignment, can obviously also only take place when the disk of the star still exists. So we'd expect that to also take place at low timescales. Indeed, we see only aligned systems at low timescales, which suggests that these effects are promising in explaining the observed alignment. So in sum, just to recap, I observed an alignment compared to a control sample. This alignment is statistically significant and previously unobserved. I came up with a couple theoretical explanations that could explain how these exoplanets went from randomly aligned with respect to the wide binary to aligned over time. So in exoplanet astronomy, we have lots of observations surrounding exoplanets and stars from the TESS and Gaia spacecraft, and we also have a lot of theory of how these planets in wide binaries could evolve over time, and in general how planets evolve over time and how wide binaries evolve over time. But we have very little studies connecting these theories to this observational evidence, and I hope my study kind of furthers that goal of having a comprehensive picture of how exoplanets form and evolve. Thank you for listening to my presentation.